So I'm going to deal with some of the features of the new release of MagNet 7.8, and I hope after this webinar you're going to have to find these features more useful to be able to help you better solve your magnetic problems. So the key main feature that we are going to discuss in this webinar is how MagNet 7.8 improves iron loss prediction in time harmonic solvers. And also we are going to introduce two types of switches, control switches that have been added in MagNet 7.8, that is current and voltage control switches. The most important thing about the iron loss prediction in time harmonic solvers is the advantage of the fast solves. Like it has higher solution times compared to transition and other solvers. And also, so if we combine or leverage the faster solving solution times with the acceptable accuracy, then we can see that designers of large devices such as transformers, inductors, and choke and reactors are going to benefit a lot from these improvement. And also, if we go to the control switches, it actually means that we can actually be able to implement complex circuits and drive circuits within MagNet. And this, the main advantage, the key advantage is without the need of a secondary circuit controller or simulator. So the main application that we're going to find for these, or the people who are going to find this feature more, is who are magnetic device designers for converters and switch mode power supplies, and also people who are trying to investigate the effect of switching effects on motors, designers of inductors, coils, and wireless power transfer. So these key two features are important and also applicable to the industry as they are. So we are going to start off with how MagNet 7.8 improved the iron loss prediction in time harmonic solvers. And generally, we can attribute this improvement to two key points: how MagNet 7.8 handles nonlinear materials, and how MagNet 7.8 estimates fields and iron losses. And we are going to demonstrate these using a single-phase distribution transformer. So if we go back to the basics and see how a nonlinear material is presented in finite element analysis, we basically use BH curve. So we have the linear region and the nonlinear region. So the core is basically presented by the core properties are basically presented by this nonlinear BH curve. And as you know that if I'm operating in the linear region, the time harmonic solver is going to perform optimally. But if I go beyond the nonlinear region, then it means that I need to estimate my nonlinearity. So if I have a sinusoidal B or a sinusoidal H field, and I assume that my core is operating beyond the knee, then it would mean that the resultant field that I'm going to generate is going to be non-sinusoidal in nature. So because basically know that the time harmonic solver is a single frequency solver and works on phasors, then it means that we actually have to try to estimate or approximate the nonlinearities. For instance, if we take the case of a sinusoidal B, which corresponds to a voltage-driven case, and assuming, because you know that in the linear region, the solver will perform as expected. So assuming that the core is sitting, or parts of the core are sitting beyond the knee of the curve, then we know that the expected H waveform is as shown in the slide. So it's going to have an added third harmonic peak harmonic, which is characteristic of a magnetizing current. And this case is unique or is more applicable because we expect transformers to behave in a similar way. So when you are doing the iron losses, you are going to connect either secondary or the voltage, depending on the supply that you have, to a sinusoidal driven source. And then the corresponding field, H field, will be the magnetizing current. So then if we go now to assume that we have a sinusoidal H, which corresponds to a current driven problem, then we expect the same behavior. But in this case, now we get a saturated B waveform, which is non-sinusoidal in nature. So what do we get from these two plots? We see that depending on the source that you are having, it's going to affect the resultant waveform. So depending on whether you have a current driven or voltage driven, you're going to have a field that are going to be non-sinusoidal. And as I said before, the time harmonic solver is a single frequency solver. So how do you then approximate these non-linearities? So how does MagNet 7.8 handle these? So I'm going to use sinusoidal B, which correspond to a voltage-driven problem, which actually correspond to a transformer. And we can see that, as I said before, if you expose your core to a sinusoidal-driven B field, the expected H waveform will be non-sinusoidal, and it has the characteristic magnetizing current. So how does now the time harmonic solver approximate this nonlinearity? So it will use any of these methods. So what we mean by that is, like, we need to transform the BH curve using 4 methods: RMS, peak, equal RMS, and best fit. So it will take the sinusoidal B that you want, and also go to your BH curve and estimate the transient H curve, H waveform. And then it will also consider whether your field is B or H, and this has to be entered by the user. These 2 parameters has to be determined by the user. Then after that, because as I said before, the key point to note is the time harmonic solver is a single frequency solver, then it will transform your non-sinusoidal waveform into an equivalent single frequency waveform. So at this point now you have 2 waveforms which are single frequencies, and then you can push them through into the time harmonic solver. Then after that, after solving, then you transform back into the equivalent transient waveforms. But in this stage, you're also considering whether your waveform is sinusoidal, B or H, and also the other capability you have, you can be able to interpolate between the 2, either sinusoidal B or sinusoidal H. And then from these, now you can be able now to transform, to estimate your fields and iron losses. And the key point to note is that the time harmonic solver is using the same method as in a transient solver. So to recap what I've just said, so assuming that we are considering a case of sinusoidal B, which corresponds to a voltage-driven case, so you're going to generate the transient waveform from your BH curve, and then you transform your BH curve based on these 4 methods, and also on the interpolation factor, which takes into account whether it's voltage-driven or current-driven, and then it will transform your non-sinusoidal waveform into an equivalent single frequency waveform, which then allows you to take into consideration the time harmonic solver, to apply the time harmonic solver. Then after that, you estimate your transient waveform, from which now you derive your fields and iron losses. So now I'm going to show some of the results that we were able to generate using the solver in MagNet 7.8. So you can see we have our core. So this is the transformer. It's a quarter model of the whole transformer. So we have our core there. We have a low voltage coil, and we have a high voltage coil. Then we can check to see the material properties of our transformer, of the core itself. So we just navigate to the materials tab, and then we can check the properties of the material making the core. So we can see the BH curve of the material. So it's at about 2 Tesla, but you can see that because it's grain oriented steel, you can see that the saturation is at a higher flux density. Then you can also see the loss data, the core loss data for this material that has been entered. So the user is expected to do the same. So you can at a particular frequency, and also you can take into account the data that you have in terms of if you have material for different thicknesses. This equation allows you to actually use all the data that you have, and then so you can use this lamination ratio and the frequency and also the temperature. So this is the equation that is used to estimate your iron losses. And what I just want you to notice that our KE factor is 0. So this data is used to fit this equation, but you can see our fit is pretty much good. It's about 0.99. So that shows our material data. So you can also see like MagNet provides a rich source of materials ranging from non-oriented steels to other types of steel, to permanent magnets, to brush materials, to competitor segments, conductors, coolants, and insulators. And if your material is not part of this list, it's easier, or you can actually add your material, and it's easily done in MagNet. So this model was set up for estimating the no-load core losses, or the no-load test. And you can see that it's voltage driven. So I'll navigate to the circuit window, and that's my supply. It's voltage driven, and it has also been scaled because the model is not a full model, it's a quarter model. And then we connect just a resistor on the secondary side, a very high resistive value, just to ensure that the current will be low, and that's our high voltage coil. So let's see how our field distribution is, the peak field distribution, the peak flux density distribution. So I will navigate to the field tab, and then I will select the shaded tab, and then I'm going to display the fields at 90 degrees, where it's the peak current, because you saw in the voltage that it's a cosine voltage, so my current will be 90 degrees. The peak will peak after 90 degrees. So this will give me the maximum peak flux density distribution in the core. And then I'll update to view my peak flux density. So the value, if you look at the distribution, we can see that the core is pretty much sitting at a very high flux density. So which is good for us to be able to test how good the solver is doing in comparison to that transient solver. And you can see the value is sitting at about 1.82935 Tesla. That's the peak value. So then MagNet has also a convenient way of giving you the global results, like the time average results. So I will navigate to the results page. And you can see you can get in a simple format the global results or average results. So you have energy, force, flux linkage, ohmic, iron losses, current voltage. And if I just click on the iron losses, you can see that it has given me a value of about 56.8, which is in the units of watts. So as I said before, because our fitting coefficient was about 0, that means like we could not generate any eddy current results. So depending on the data that you give to the software, then it implies that it will estimate your losses depending on the data that you give it. So with this implies that when you are putting in data into the material, when you are defining your materials, it's very critical to consider the point of operation of your material and the data that you are using. So I will note the value is about 56.8, and our value for the peak flux density was about 1.82935 Tesla. So how do these results compare now with the transient solve? So it's the same transformer model, but in this case, it's sold as a transient. So I'll go to the results page. I just want to show my assumption at the outset. So that is voltage driven, and I can see that my voltage driven is highly sinusoidal in nature, which is as expected. And then the current, it has the characteristic magnetizing current. So this is a good case for testing how well magnet time harmonics overestimate the losses. Then I'll display the peak flux density in this case. So I'll do the same thing. I'll navigate to the field page. Then I'll pick the time when you have the time instance when you have the peak current. In this case, I chose 45.833. And then I'll go to the shaded and I'll update my view. So similarly, you can see that we're able to approximate or estimate the same flux density or achieve the same peak flux density of 1.82933, where the other one, the difference is only in the last three digits, 35 and 33. So the distribution is similarly the same. So I would expect also the iron losses to be similarly distributed. So then I'll navigate to the results page, the global results page, to generate my average iron losses, and you can see that the value is 57.3. So if I compare, then I get 57.3 from the transient solver and 56.8 from the time harmonic solver, and the peaks are similarly the same. Then you see that there's a gain in terms of accuracy, and also leveraging the speeds of a time harmonic solver. So then let's navigate back to our PowerPoint, and then we can summarize the results in a slide in the next subsequent slide. So we from the demo we were able to see that the time harmonic solver can actually predict the same peak flux density, and if you can actually estimate the flux density, then it means that we can also estimate the iron loss distribution, and this is well summarized in this table. So it in terms of time, solution time, it takes about 3 minutes to solve this problem. And at this point, I've also taken into account about the model. So I've scaled the results from the quarter model to the full model, and then the transient solver takes about that 3 minutes. So this shows the gains that you get. You are able to leverage the fast solution times of a time harmonic solver, and then by MagNet 7.8 improving the way to estimate non-linearities, you're able to achieve the same iron losses, which is a good gain. Now we are going to switch gears and go to controlled switches, that is current and voltage control switches. The key advantages, as I said before, is that it allows us to implement complex control and drive circuits that we previously could not do. And also the other advantage it has, it allows you to do that without the need of a secondary circuit simulator. So we can be able to implement now circuits like PWM-driven circuits. So you can do sine PWM for motors or for DC to DC converters. You can also implement hysteresis controllers, and also you can use the current or voltage ratio to be able to effect your switching transitions. So these icon shows the voltage control switch, and if you double click or expand its properties, this is the window that you're going to get. And to be able to implement these strategies of circuit control, you just need to modify these four parameters. Some of them will be active at one particular time, or others will not. And you can actually determine also your initial state. We also had, this is in addition to other circuits, does not mean previously we did not have switches, but we had switches, but some like position control switches and also other switches. But the key difference is you had to know when to transition the switch or when to activate the switch. But in this case, you don't have to know. You can actually use the circuit or the current or the voltage in the circuit to be able to effect your switching transition, which is basically you can be able to feedback and be able to do it within the circuit, and all that is within MagNet. So to be able to capture the whole spectrum of application of webinar audience, I'm going to use this generic inductor model to explain some of the features that you can use with Infolytica products. So here we have a micro inductor, which also shows you the capability of MagNet to simulate devices from the micro scale to the macro scale. We can see the input trace, the output trace, the substrate, and also the conductor. And also we have the core, and we have explicitly modeled turns. So one may want to estimate the parameters of this inductor. So in this case, now it depends on the operating frequency or the operating range of your device. So if I'm interested in inductive and resistive components, then I can use MagNet to be able to estimate the parameters of this device. If I'm interested in capacitive components, then I can use ElecNet to be able to do the same. And if I want to see how temperature affects the device performance, then I can couple the solves to a harmonic. So depending on the operation, which now depending on the range of the webinar attendees that we have, so some of you may be working at low frequencies or DC frequencies. So then it means that you can neglect the AC, and you get one of the hysteresis component for the ALCO. ALCO represents the core losses, DC represents the DC resistance, and AC represents the AC resistance of your winding. And LS is what actually you're designing your device for. And this is the capacitance or the stray capacitance that we get between the input, the output, and also the interturn. But this basically depends on the operating frequencies. So an inductor like this is a good representation of what someone would, depending on the operation, and how they can use the packages that we have to be able to achieve their goal. And also you can couple them to get a truly multiphysics approach to their problem. So then, because you know that mostly when you're doing coil design, inductor design, mostly you use an analytic approach. We know that's the most used method, which is okay. And you can use it to initialize your devices. Why then do you want to use finite element analysis, or why do you want to use MagNet? So basically, the main reasons is because analytic methods do not fully account for these effects, such as switching effects, core non-linearity, skin effects, load variation, fault analysis, capacitive effects, which require you to use ElecNet to be able to estimate your capacitance. Then hotspots, if you want to see your distribution of your fields, your losses, then it's good to use finite element analysis. Then if you're also analyzing the gap effects, stray, which you affect your fringing flux and also leakage fluxes, then finite element analysis is going to capture all that, and also the 3D effects. And the advantage of finite element analysis, or the advantage of using MagNet, is most of these effects are captured in just a simple 3D model. It can be able to give you all those effects. But if you have to do all these analytically, then it will complicate your model. So the key advantage of MagNet 7.8, or the improvement that we have with 7.8, is we are able now to take into account the switching effects when we are modeling our devices. So this is an example of a boost converter that is boosting your battery voltage to the DC bus, and we are mimicking the load using a simple resistor. So this is able to capture most of the effects except the capacitive effects. So what I said before, the advantage of this switch, the control switches, is you can use any voltage to control the switching transitions, which allows to give you feedback, or you can use any current through any of these elements to be able to control your switching transitions. And we are going to see how we can actually do these for boost converter that you can employ in electric vehicle drive. So as an example of how how it's easier to analyze some of these effects in finite element analysis in magnet as compared to if you are to do the same uh, if you are to achieve the same analytically. So this shows how an example is skin effect. And we know that skin effect literally reduces your flux curling capacity of your core, or it actually reduces your current curling capacity of your conductor. So basically, you'll be sitting around with the conductor, curling it around, especially for mobility problems, mobility applications, where the inner regions or the inner portions of your conductor are not curling any current, but they are they have weight, so you're going to be spending some energy to, if in case of mobility applications, and the core, which is also the same. So if you're working with high fundamental frequencies or you have high order switching harmonics, you may want to estimate your conductor losses. And also it's a good thing to be able to estimate your conductor sizing. So to be able to know how much you want to strand your coils or to size your core. In this case, to size your magnetic core. The advantage of a magnet is that it has a simple way of doing that. So you don't have to apply the mesh layers to the whole component. You selectively apply it to the surfaces or faces that are predisposed to the skin effect, as shown in this model. So we know in this case, the top face and the inner faces are the ones that are predisposed to skin effect. So we apply mesh layers, and as you see in the zoomed in version of the corner, then you can see that we have the fine mesh layers that are able to emulate the skin effect. And then you can have huge mesh settings for the rest of the component, which increases your numerical efficiency. So now, how do I now, if I wanted to implement controlled circuits? So in this case, let's assume I want to control my inductor energy or the energy stored in an inductor. So I can do that by controlling the current in the inductor. So in this case, I will take a value and say I want to control it at about 40 amps, and I want my hysteresis band to be about 10 amps. So my excursions are about 5 amps positive or 5 amps negative. So I can move between 35 and 45. So at this point, I'll switch on my inductor, and then at this point, I'll switch off. And at this point, when the current decays, the inductor current decays to about below 35, I'll switch on the inductor, and then after that, I'll switch off. So we can implement that in magnet as seen in this circuit. So we have our inductor there that is a 3D model, so it will be able to capture most of the effects that I mentioned about. And then I've connected it in series now with my current control switch, which is hysteresis controlled. And then I can be able to regulate the boost properties of this converter. So typical results that I would have expect if I was analyzing this kind of a problem is as shown. So this shows the total loss distribution on the core. This is an 8 mode of a nickel inductor, and this is the coil. So if you look, you can see that the loss in the coil is pretty much close to zero, or is uniformly distributed. This is because in this case, I'm using stranded coils, which is another advantage of magnet. So it means that, and this is a good assumption and a practical assumption, that if you have well designed the inductor, then it means you have been able to suppress your AC losses, and only you are left with the DC losses. So to be able to estimate my DC losses on the winding, and it will uniformly distribute the current within the turns. And then it means that now I can be able now to analyze my core or design my core as appropriately. And then the other key advantage of magnet, another feature that is important in magnet, is that I can determine my window for analyzing the losses or for averaging the losses. So at the face value, it might look like it's not important, but if you are doing fault analysis, or you are doing transient analysis, or you are doing load variation analysis, then it's an important key feature, because I can determine my averaging window depending on where I want. and with that, I can be able to analyze the impact on my device. Is my device still within my design window, or does it still meet my design criteria? So the advantage of that, and then combining with the uniform distribution, is I can be able to estimate my hotspots, and I can know where my sources of heat are, and can I actually be able to take them out at the required time with the time that you are given. So let's assume now I wanted to control the voltage, my output voltage. So seen here. So this is my battery voltage, and this is my output resistive voltage across my output resistors, which is basically the output. I can implement that using this circuit. So this is still my 3D model represented in the circuit. And then I can use a PWM voltage control switch to be able to time my switching transition. In this case now, I can be able to test different duty ratios on how they impact my device performance. Yeah. So I just need to connect a voltage source with my duty ratio, or alternatively, I can connect a voltage, either the load or across the capacitor or across the inductor, and I can be able to control the switching transition of the switch. So we have similar results as the previous case for current control boost circuit. So we see the total loss density distribution, and we can see that in this case, our currents are extreme, they are higher. So we have about 180 or about 200 between, and then we are settling at 0. And then this, in a similar way, you can determine your averaging window for the losses, and you can see the loss distribution. So if I can have a generic comparison, so at the face value, we have this case gives us a higher loss than the other, and I can actually be able to decouple the copper losses and the iron losses. At the face value, it's a good comparison, but the key point to draw from these is in MagNet, it allows me actually to, if I have different switching schemes that I want to compare, I can be able to analyze them in terms of the device performance and also the loss distribution and also the global results, or the average, the time average losses. The other thing to consider is, or the other advantage of using MagNet and the averaging windows move, if determining the location of the averaging windows, is that I can be able to do transient analysis and also be able to evaluate my fault analysis. And because we know that switching transitions are going to affect your transient performance of your devices, then you can be able to you'll be able to better represent your device performance and see whether it's meeting the design criteria that you set out. So in summary, we saw that MagNet 7.8 has improved the error loss prediction in time harmonic solvers, and this can largely be attributed to two main factors on how it handles the non-linearity in core materials and how it estimates the fields and iron losses. The other is also we introduced new controlled switches into our circuits. So, and we can be able now to implement a PWM-driven circuit, hysteresis-driven circuit, or we can actually use the current or voltage threshold to determine the switching transition.